Welcome to BC Gnomonics. In this video, we're going to be explaining exactly how the equatorial ring dial is able to self-orient. Now to begin, we won't be looking at the equatorial ring dial itself, but a much simpler form of equatorial dial, the equatorial bowstring. Now, in its normal everyday use, the equatorial bowstring is considered a stationary dial, with the inputs being a northern orientation and a latitude setting, and the outputs being the date and the time. At least for this style. Not all equatorial bowstrings can indicate the date. Now let's use our model sun here to demonstrate the typical function of the equatorial bowstring. So imagining that we've oriented it for true north, we can read clearly that it is 10 a.m. at the summer solstice. If we were using this simply as a stationary dial, this would be the end of our reading, and it would be quite a simple procedure. However, since this is a smaller model and it can be manipulated in space, let's turn it into a self-orienting dial, in a sense. So pretend we don't know the direction of true north, but we do know the date. So knowing that it's the summer solstice, how do we orient this dial? Well, we simply rotate it until we see the notice line up with the current date. Now, if you're familiar with the function of portable dials, you may realize that there are two spots where this will occur. Right here, indicating 10 a.m. at the summer solstice, and right here, indicating 2 p.m. These two spots appear to be equally valid, but only one of them will indicate the correct time, the other being the same hour, or the same solar elevation as the correct hour, simply mirrored across in the other portion of the sky. For example, 10 a.m. and 2 p.m. have the exact same solar elevation, except in the case of 2 p.m., the sun is in the western portion of the sky versus the eastern portion of 10 a.m. So if you're using the dial in this self-orienting fashion, you simply have to know either the rough direction of true north or whether the reading is being taken in the morning or afternoon. In this case, let's pretend that we're taking this in the morning, so 10 a.m. is the correct reading. Now, we can take this a step further. So imagine that this dial, the hour plate of this dial, is only as wide as the equinoctial ring. So as the equinoctial band. So we only have this central band of hours as our hour scale. Everything else is cut away except for a central strip running along the equator. In this case, we can no longer use this self-orienting method as it requires a full declination scale as well as a fixed central notice. But if we try to do our same procedure here, well, first of all, there'll be no date scale. We can't. If somehow we could imagine the date scale, the notice would simply fall off the plane and nothing could be read. So what we need in this case is a movable notice that will fall on the equatorial line when the correct time is being indicated. And the way we do that is by switching the date scale, translating it from the hour scale itself to the polar gnomon. So now, rather than having our date indicated by a feature on the face, it is now indicated by the position of a movable notice that will account for changing solar declination. So right here, you can imagine this little star as our new notice. You can completely disregard the fixed one. And you can also imagine this notice as being at the topmost region of its date scale, indicating the summer solstice. This date scale is functionally identical to the declination scale on the equatorial ring dial, with the setting for the summer solstice resulting in the notice, in this case the gold star, being positioned 23.4 degrees above the plane of the equator. At the winter solstice, this star would be positioned at its lowermost end of the declination scale, 23.4 degrees below the equator. So here you may start to notice similarities between this model and the equatorial ring dial. as both feature a sliding notice that moves along the central celestial axis. In this case, again, pretending that the hour scale is no wider than the equatorial line, we can do the exact same procedure, except this time it will work with this reduced hour plane. Again, as we rotate, if we know the date, we see that the times that line up are 2 p.m. and 10 a.m. If we know that it is currently before noon, we know that 10 a.m. is correct. Now let's do the exact same thing, except at the winter solstice. So in this case, we'll have to translate our notice down to its southernmost region of the declination scale. And now, again, we know the date is the winter solstice, so we simply rotate the dial until that notice falls on the equatorial plane, which again happens right here and right here. So in this case, this portable dial that we've created is, in every respect, functionally identical to the equatorial ring dial. We had to go through a couple conceptual leaps to get there, but if we imagine the equatorial ring as the only hour scale, everything else cut away, and there being a movable notice that moves between the extremes of its declination scale, we have, in essence, an equatorial ring dial. But this model doesn't have to be conceptual, as there is a dial that functions in this exact same way, which is the crescent dial. Now, we'll be using the afternoon hour scale for this demonstration, but as you can see, exactly like in our model, we have an hour scale that's only as wide as the equatorial plane, no room to capture changing solar declination. Instead, the declination is accounted for by a central movable notice. So right now, this notice is set for the summer solstice, and as such, will capture the shadow on the hour plane when rotated into the correct position. If it were the winter solstice, which we can easily model, the exact same procedure can be followed. And as you can see, I'll just tighten that so it stops falling down. As you can see, the notice in this case is quite a bit south of the equatorial plane, just like on the model, and just like on the equatorial ring dial at the winter solstice. And again, it functions exactly the same way. So in this case, the date is set using a central notice. The notice is set to a position below the equatorial plane, and for the correct time to be displayed, the dial simply has to be rotated so that the notice falls on the plane of the equatorial plane. Again, there will be two positions where this will happen. You simply have to know which one is correct. But this demonstrates that the exact same concept that underlies the equatorial ring dial can be made in a stationary form. And even in a stationary dial, in the case of a stationary dial that is not made to be self-orienting, we can apply the principles and, as we did, turn it into a self-orienting dial. So hopefully this has shown the principles that underlie the equatorial ring dial's self-orientation. And I thank you for watching.